All right, everybody, this is chapter 14, all about chemical periodicity, which is basically saying the trends of the periodic table. Um, our textbook doesn't have everything in the best order to remember them, so you'll see that we did chapter 5, then we did chapter 28, and then we did chapter 13, and then chapter 14. Okay, so this was our atomic structure, then we did nuclear, then we're talking about electrons, and now that we have everything done for our elements, now we can put it all together and talk about the periodic table. All right, and one of the things that I want to point out to you is what we're starting off with is technically in section 5.4, the end of chapter 5, but we're going to put it in this section of our notes and with our properties. Okay, and that goes with who the father of the periodic table is, and that is Dmitri Ivanovich Mendeleev, and he was the first person to organize the elements in a chart. Okay, so this is a very, very long time ago. So what I want you to remember is that at this point, there's really only about 70 elements out of the 104 naturally occurring, and now we have some unnatural or man-made ones, and now we have 118. So he said, let's put them all together in some useful tool. And let's see if there's any kinds of patterns. So he put them in terms of atomic mass. He didn't really know their protons weren't discovered yet. The atomic number wasn't really a thing. And he figured out that if he put them by increasing atomic mass, there were some trends. There were some patterns. So much so that he left blank spaces for undiscovered elements, which people thought he was cray-cray bananas about the whole thing. So here is Mendeleev. Like I said, he was Russian, so everything is written with the Cyrillic alphabet. And hydrogen with a mass of 1 went first. Lithium with a mass of 7 went next. Helium wasn't discovered yet. Then we have beryllium 9.4, which in Russian and in European countries they use commas for decimals, which is very annoying. My mom is from Poland and she does that sometimes and it always messed me up. Boron is 11, carbon's 12, nitrogen 14, oxygen 16, fluorine 19, sodium 23, and not exactly the most logical of all numbers. But what you'll really see that is very interesting is that he leaves blank spots. There should be an element with a mass of 45 to go in here. And maybe these elements that aren't really discovered or known too well or not known enough are going to go here, there, and the other thing. And you're going to see all these question marks and these blank spaces. So you're going to see that these blanks are actually going to be the undiscovered elements. People thought that he was crazy. They're like, no, down with Mendeleev. And he was like willing to basically bet it all on it. And guess what? He was right. Okay, Henry Moseley, which was a British scientist, he ended up taking all of that awesome work from Mendeleev and improved upon it. Instead of arranging things by atomic mass, he put them by atomic number because the protons were discovered at this point. Okay, and he also found that there were similar properties, and he left blank spaces as well for undiscovered elements like helium and that kind of stuff. He also found that you can't have an element that's lighter than hydrogen, which was a pretty important discovery at the time. Okay, so it's a good thing that Moseley ended up rearranging the periodic table, and I'll tell you why. All right, take a look at our potassium and our argon. Potassium's number 19 comes after argon, number 18. But potassium has a mass of 39.10 and argon is 39.95. If we would have left Mendeleev's arrangement, okay, the argon gas would be lined up with the metals, and the metal, potassium, okay, would be over with the nonmetals. So it makes more sense to have this common arrangement of increasing number. It also makes it a lot easier to read with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so please bust out your periodic tables. We're going to be using it a lot this entire chapter. You want to make sure that you're looking at it and writing notes on it. Okay, groups or families are the columns on the periodic table, and as you read them, there are 18 groups or families, and yes, they have things in common. Periods a row, there are only 7. It's not 9. Those bottom two, the lanthanide and the actinide series, or the lanthanoids and the actinoids, they actually go up and into rows 6 and row 7. And it's because of this arrangement by Moseley that we see this repetition of their physical and chemical properties, and the name of our chapter, that periodic law. So you'll see that periods are repeating and happen in a predictable fashion, just like on our periodic table, periods of the day in class, female periods, don't cringe, but they are predictable and repeatable. So here are our 18 different columns, okay, our groups, and they all have special names. And in the next video, we'll go over what each one of these is, okay, with the alkali metals, alkali earth metals, our transition metals, our lanthanide and actinide series over here. Then we have some other elements, our metalloids, our other nonmetals. Then we have our halogens and our noble gases. Okay, but basically what we're seeing is that right here with this right here with this diagonal line, okay, that you see, okay, this splits our periodic table up into 2 parts, all right, and that is going to be, our metals on the left-hand side and our non-metals on the right-hand side, with our metalloids having properties of both in between. Now, there's lots of different kinds of periodic tables. Some are like this tower periodic table that you see here, and here is this crazy cyclical one. Yes, it works. People put this circle one. This is actually going to be what Mendeleev kind of started everything off with his flower model, because this was the S, the P, the D, and the F orbitals relating back to last chapter, S, P, D, F. So it's really kind of interesting how the whole thing comes about. Our modern periodic table has the lanthanide and the actinide series down at the bottom, and they go in here. Um, that's why it's written kind of below. And if it weren't, they would have to have this huge bubble over here. So in my classroom, I have the S orbitals here. Then I have it cut out for the F orbitals to go there. Then I have the D orbitals, and then I have the P orbitals like so. It doesn't fit on a normal sheet of paper that's readable, but it does kind of help when you start looking and going across each row, because you see a repeatable, predictable pattern as you travel across your periodic table. All right, so like I said, we have that special jagged staircase, that line of demarcation that separates the left and the right. Okay, the metals are on the left, the non-metals are on the right, and the metalloids are along those lines. They have very distinctive properties. The metals are going to conduct electricity and heat, not like an orchestra conduct, but like actually be able to flow electrons from one end to another, from the negative anode to the positive cathode. They're malleable, which means that we can change their shape. They're relatively strong. They have very high melting and freezing points, so you're going to see that most are solids. Do you know what the liquid one is? That's right, it's mercury. And they have luster. So if you are a friend of Moana, that is shiny. Oh, Moana. I've seen that so many times with my kids. All right, then we have our nonmetals, which are the exact opposites. They are going to be insulators. They do not conduct electricity well. They're going to be brittle and relatively weak, with low melting and freezing points relative to the um, metals. Most are going to be gases, some liquids. The liquid one is bromine in there, and they're dull. They're not shiny. Okay? And then our metalloids have properties of both metals and nonmetals. Okay, so our metalloids are these. Here is the actual line of demarcation on the periodic table, like this. All right, so the elements that are actually going to be our metalloids are going to be boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. They, like silicons, can have properties of both nonmetals and metals, be semiconductors. They sort of do, sort of don't. That's what we have in all of our computers. They conduct electricity like a metal, but they're going to be brittle like a nonmetal. So, they're both positives and negatives to having and using those. So you have to use them for what you need. All right? So stay tuned for our videos about our cavities.